Hello everyone, am I audible? Thanks for the confirmation. Hi, good morning all. Actually, today Sunny sir is not going to join because I think if you don't know, he had an bike accident. Okay, so that's why he won't be able to join today. So no, sir is fine. Just it was a little injury. Okay, so see, actually he has another session, so he won't be able to continue with this long duration. So that's why I joined this batch. Okay, so I think you can consider. Yes, I will be taking the entire session. Okay. So today actually we are going to discuss about the CNN architecture. Okay. I think this is going to be your first session on CNN architecture, right? As of now, you have covered the basics of CNN. Am I right? I'm not sure actually if like Sunny sir, like if he has some work or if he is not able to take any session, then I will be coming. No issue. Okay. Today we'll be explaining about the CNN architecture. Like as of now, we have learned the basics things like you have covered this thing like convolutional padding, stride. Okay, then pulling. These are the things you have covered, I think. Okay, so now how we can use them to create architecture. Okay, actual architecture. If you see any classification, image classification, you can say algorithm or you can say model. You'll be seeing they are following one architecture. Okay, this architecture has researcher have developed. Okay, so we'll be discussing like how they have developed. Okay, and if you want to create your own architecture, so what are the things you need to keep in your mind? Okay, so this thing actually will help you to understand. Hmm. Okay, guys. So just focus on the session. Okay, because this is going to be a very important session. Because here we will be starting with our like first introduction of the architecture of CNN. Yes, theory. Like once theory is covered, suppose I will be discussing three architecture. Okay, if time allows. Otherwise, I will be just as of now just cover two architecture. Like if you have heard of or not, like LeNet and Alexnet. Okay, I'll be telling you what are the architecture I'll be discussing. So after that, I will be showing you like how to implement using Keras. Okay, I will show you the coding part also. No issue. Don't worry. Like implementing with the code, so it would be neat and clean in your mind, like how things are working. Okay. Actually, myself, my name is Bukhtiyar Ahmed Bappy, and I am working as a junior data scientist in iNeuron. I think most of them you know me if you are connected with the LinkedIn, and I think some of our yeah, because I haven't came to your batch like you can say previously. Mm. No, actually, I'm from Bangladesh. I'm not from India. Yes, I'm sharing my LinkedIn profile also. Just recently, I visited India. I went to Bangalore actually to visit my company. Then I came back again here. This is my LinkedIn profile. Okay. So I'll be telling you today's agenda. Okay, so don't worry. Yes. Okay, guys. So let me share my screen and just confirm once you are able to see. Yeah. Yeah, I think my screen is visible. Screen is small. I'm using my big monitor, I think. You can see my whiteboard, right? Yeah, I haven't written something. I will zoom, no issue. Hmm. Okay. I think my audio is fine, everyone. Can you hear me properly? Is there any noise you can see? Okay. Mhm. Okay, so don't like you can say focus on the chat, okay? Yeah. So let's start with our like agenda. Okay. So I'm turning off my camera because just focus on the board, whatever I am writing. Okay. Mm. So today's agenda would be will be architecture. Uh, am I audible, guys? Okay. Mm. So CNN architecture, we are going to discuss in this session. Okay. So we'll be seeing like there are many different like CNN architecture are available, and you will be using them. Okay, for sure in our day-to-day life. Okay, if you're working in the field of computer vision. Okay. So and this thing actually will remain same. Okay, if you are doing and if you're learning also object detection and segmentation. Okay, this thing will remain same. Okay, this concept will remain same everywhere because today's agenda is like we are still learning the classification, okay, image classification things. And I think till now Sar has discussed the basics of CNN and he has created some vanilla CNN architecture. Okay, and he trained like this one your handrest MNIST classification model and all, right? So this thing as far you have done, but this vanilla architecture won't work. Okay, whenever you will be picking some complex data. Okay, so for that you need some architecture. Okay, so well architecture. So this well architecture is already there in the Keras. Okay, or you can tell like it is already available. Okay, with us like as a pretend weights also. I will show you like what is pretend weights and all. But before that, I just want to discuss about the history of CNN architecture, like how it came. Okay, in the like field of computer vision. Yeah. So now just for a, like you can say revision. I just want to tell. I think am I right or not? Just tell me. I think you have covered uh, convolution. Convolution. Okay, I think you have covered this one. Then I think you have also covered the padding and stride. Okay, stride. Then I think you have also covered pulling. Okay, this thing I think you have covered. Everyone. Okay. Okay. So now, if I talk about just for a revision purpose, as of now, how you used to create a CNN architecture. Okay, like vanilla CNN architecture. So if I tell you just how you can create a basics CNN, okay, convolutional neural network, basic CNN, how is to create. So first of all, I think so I think you used to take an image first of all. Suppose this is your input image. Suppose I am taking one RGB image here. Okay, so the image dimension is suppose 32, 32, 3. Okay, this is one RGB image I am taking, and this image used to pass to a convolutional layer. Okay, suppose I'm taking one convolutional layer here. Suppose with the filter size of suppose there is a filter size of 3. Okay, I'm taking. So let's take. So like you can say filter dimension would be also 3 because I have 3 channel image here. Okay, so this is one filter. This is another filter. This is another filter. Okay, so our filter size is 3, 3. Okay, and this is our convolutional layer. Suppose this is convolutional layer 1. Okay, after that you used to pass this output. Suppose after doing the convolution, what you will get? You will get something called feature map. Suppose this is the feature map I got here. This is a volume. Okay, this is a volume, and we call it feature map. Okay, and here you used to apply also, I think, some non-linear actually activation function. Suppose ReLU, I think you used to apply. Okay, so this thing actually basics I'm expecting, and after that you used to take a pooling layer. I think if you remember, there is a concept called pooling, max pooling, average pooling. Okay, then these are the pooling you have. Suppose this is the pooling layer. Okay, so let's name it pooling layer. Pooling layer 1. Okay, so this is my pooling layer. After that, what you will get? You will get a tensor again. Okay, suppose this is the tensor you got, and you can repeat this task. Okay, so you can again feed it to your convolution into contour layer. Okay, then again what you can do, again you can pass it to your pooling layer. Okay, pooling layer, you can do it repetitively because there is no hard and, like you can say, restriction, like you can't use convolution layer twice. Okay, you can use it, it's up to you. The way you are creating the architecture, it's totally up to you. Okay, suppose this is my architecture. Okay, this is my final architecture. Now what I used to do, so I used to take this feature map. Okay, I used to take this feature map, and if you remember, we used to convert it to something called flattened layer. I think you know this concepts of flattened layer. So the main concept is to flatten layers to convert each and every tensor is to one-dimensional array. Okay, so this one-dimensional array, what we used to do, something called, there is a NN. I think you have learned the NN, like that means fully collected neural network. So we used to define a fully collected neural network. So this is my fully collected neural network. Suppose I'm taking. Okay, so suppose this is my output. Okay, this is my y hat. That means output. Okay, so now this flattened array I used to pass to my dense layer. That means fully corrected layer. Okay, this is my fully corrected layer. That means ANN. Okay, artificial neural network you have learned. And suppose this is my binary classification I am doing. Suppose this is a you can say dog or cat, or you can say 0 or 1. Okay, this is the That's why here, suppose I am using sigmoid function, and I am getting the output as y hat. Okay. So these kinds of architecture, I think you all have built till now. Just confirm me in the chat. Have you done this? Right. Okay. So see, this concept is remain same everywhere. If you see, this concept will remain same everywhere. The thing you have learned, it's fine. Okay. Because this thing actually, it is required to understand the CNN architecture, because see, CNN architecture is nothing but it's just a variation of this architecture. That's it. So how people came up with the different CNN architecture. Okay, now let's discuss about that one. So let's take my pen. So I'm talking about people. People means what? Researcher. Okay, because researchers have came up with a many architecture as so far. If you see, there are many misclassification algorithm you will see, like VGGNet, Inception, then Alexnet. Okay, then you have ResNet. These are many, I mean, architecture you have, but how they have came up with the idea. Okay, so what they did, so changes the architecture by, so what they did, they suppose uh, added some convolution layer, or decrease some convolution layer. They added some more filter. Okay, filter. Okay, suppose they did some modification on the stride. Okay, then they did some modification on the padding. Okay, all the small thing you have learned, that can be utilized to build a big architecture. Suppose they have done some modification on the nodes. Okay, suppose you have fully connected neural network nodes, you have dense layer. Okay, these nodes, they have did some modification. They have changed the activation function. Okay, then they did some modification on dropout. Suppose they added some dropout and all. Okay, then they added some, suppose, batch normalization. Okay, so these are the changes actually they have done in the, like you can say, CNN architecture. Okay, and they have came up with a different architecture. Now the question is in your mind, why they have came up with this architecture? Okay, what was the reason? Okay, because we had a vanilla architecture, it was fine, but why they have came up with this architecture? Okay, now let's discuss it. So I think you remember there was a competition is going on called Imagenet competition. Okay, have you heard of this Imagenet before? Anyone here? What is Imagenet? Can you tell me? Okay, you don't know. Even have you ever used Shifar 10 dataset, or like you can say Shifar 100 dataset, anything? Okay. See, ImageNet is a dataset name. Okay, ImageNet. Suppose in the field of classification, okay, image classification, there is a big dataset. So this dataset is collected by millions of people over the world, and they have 1,000 class. Okay, 1,000 class in this dataset. Okay, so we call it a ImageNet dataset. So let me show you also. Just starts about ImageNet. Okay, image dataset. Okay, just starts. Actually, it's a very big dataset. If you see, this is the official of ImageNet organization, and here actually you can see ImageNet is an image database organization according to WordNet. Okay, hierarchy, and it has almost 1,000 class. Okay, 1,000 class are available. Suppose what are the picture you can consider in your mind? Suppose people, bird, aeroplane, bicycle, everything is present here. Okay, so let me go to some other website. I can open the Wikipedia. Yeah, so you can read about the ImageNet dataset. Okay, so it's a big dataset, and you can't actually download this dataset if you have like you can say low configuration machine. Okay, so ImageNet was a dataset to like you can say compete this competition, because based on the ImageNet dataset, you need to create an architecture, you need to create a CNN architecture, and that will provide a better accuracy. Okay, so that was the main competition. Okay, of this you can say challenge. So what? So what they did actually, there were many researchers they participated in this competition. Okay, and they had implemented some kinds of CNN architecture. So let's call it of history of CNN architecture. Okay. So what was the history of CNN architecture? So the first CNN architecture was something called, they name it LeNet. LeNet. Okay. So we also call it LeNet 5 because it has 5 layer. Okay. Then the second architecture they have developed called Alexnet. Okay. Because when they first of all created this LeNet architecture, so it was performed this competition and it has achieved the good accuracy. Okay. Then it was not that much of good. Then what they did, they created this one called something called Alexnet. Okay, this is one of the architecture. Okay, now there is another architecture called VGGnet. Okay, so it has some variation called VGG 16. I think you have heard of, and VGG 19. Okay, so it has two variation. VGG 16. VGG 16 means it has 16 channel, 16 layer. Okay, and it has 19 layer. Okay, then there was another architecture called Inception. This architecture developed by Google. We also call it GoogleNet. GoogleNet. Okay, so it has made by Google. Google researcher, they have implemented this algorithm, or you can say this architecture, and this is a pretty good architecture. So nowadays, actually, we also use this Inception architecture, and it's like a big architecture. And apart from that, there is another architecture called ResNet, and it has been implemented by Microsoft research team. Okay, Microsoft research team. So, and there are many more. Okay, if I name it, there are many more. If you want to like ask me, just show me, there are many more. Just search Keras application. Keras application in the internet, and you will see there are many variation of architecture. You will see. Just open the first website and see. These are the architecture you have so far. You have ResNet, you have MobileNet, you have DenseNet, you have NASNet. Okay, you have EfficientNet. There are many more actually. So we are not supposed to learn each and everything, because if we have understanding on this now, this 1, 2, 3, 4, 5, this 5 architecture, okay, rest of the thing we would be automatically understand. Got it? So far everything is clear. Just confirm me in the chat. Okay. So now in this session, I'll be discussing about this LeNet 5 and Alexnet. Okay, so I will show you when they build this LeNet architecture, what are the things they have, like you can say, keep in their mind, and when they came up with the Alexnet, so what are the changes they have done here? Which link you want this Keras application, right? Okay, I'm sharing in the chat. Yeah. So this is the link. So now let's discuss our LeNet first of all. Okay. LeNet. So first architecture we'll be discussing about LeNet, because this was the first architecture. This was the first architecture in the field of CNN. Okay. LeNet 5 architecture. Let's discuss it. So what is LeNet first of all? LeNet is a It's a classification architecture. Classification architecture. See, LeNet is not in Keras because it was like very basic architecture. Okay, so this thing actually not required. If you have some good architecture, then why will be using LeNet? Because LeNet was the first research, and using LeNet, they have came up with this big architecture, right? So you are not supposed to add the LeNet. LeNet, you can like you can code it using Keras very easily. It's two to three line of code. Okay. Okay. So it's a classification architecture, and it is from a paper called the paper name was Gradient Based Learning. All this architecture for images only. Yes, all this architecture for images only. Okay, for image classification. Got it? Because classification is the first backbone, and this classification architecture you will be using inside your object detection also, in your segmentation also. Okay, because this is the root thing first of all you need to understand if you want to deep dive in object detection and image segmentation. Okay, and if you see here your ANN is also being utilized. Okay, if you see in CNN also we use ANN in the last layer. Okay, we call it as a dense layer or fully connected layer. Okay, everything is integrated. Okay, so the paper name was something called gradient based learning. Okay, so the paper published because this architecture you can say first implemented just for document recognition, something called document recognition. And it's a very efficient for handwritten character recognition, you can say. Okay, handwritten character recognition, and it has been like first when they came up with this solution, so they made it for US Navy. Okay, US Navy. There is an organization called Postal Service. Okay, Postal Service in this US Navy, Postal Service. So they had some kinds of pin code. Okay, so they had some pin code they used to get from their machine, from their computer. Okay, so what they used to do, they used to actually classify this pin code manually. It was kinds of hard task, so they wanted to automate this thing. Okay, so they built some kinds of application using this LeNet, something called pin code recognizer. Okay, recognizer. So pin code is nothing but what? It's kinds of handwritten digit or computer generated digit, right? It's just a character or number. Character, or you can say number. Okay, it's a number. See, MNIST is a handwritten digit only. Okay, but here they used to also use the character also. Suppose ABC something called. Okay, and handwritten means what? Handwritten means it is handwritten data set. It's not like a computer written, like you can generated text. Okay, so we call it MNIST like handwritten digit. But here actually it's a pin code. It is computer generated pin code. Okay. See, you can also apply to detect the number. You can easily do that. No, pin code recognizer. See, pin code recognizer is what? Pin code recognizer, it's just an architecture they have used to recognize the pin code. They collected this pin code, like you can say image, okay, and they trained a model with this LeNet. Then if you pass a new pin code, it would be able to recognize, suppose there is a pin code, suppose A5021. Okay, this is a pin code, suppose, okay. It is able to recognize, okay, correctly. So we called it pin code recognizer, okay. And it was for US Navy, okay, US Navy. So there is a service called postal service, okay, postal service. So they had to actually collect this pin code, okay. So then this architecture has been created for this work purpose only, okay. So now let's discuss about the author, actually, who created this architecture. Authors, okay. Who are the authors actually? The first architecture they have developed, I think you have heard of Ian LeCun. Anyone heard of Ian LeCun here? He's the father of computer vision, you can say. Yeah. Okay. Then there were another man called Leon Botu. I don't know how to spelling, but let's consider Botu. Then there is another author called Yushu Bengio. Okay. So he's another like great researcher. And the last author was like Patrick Hafner. Hafner, okay, Patrick Hafner. So these are the author actually. So they have actually implemented this architecture, okay. Gradient based learning, and it was published in proceedings of the IEEE, okay, IEEE in 1998, okay. So this was the year they had published this paper, okay. The paper name was, I'm sharing this paper with you. Just wait. This is the paper actually, guys. Name is Gradient Based Learning Applied to Document Recognition. Okay, so this is the paper. You can open it up. And I'll discuss each and everything. Don't worry. Just focus on here. Okay. So this is the publishing date they have done. And this architecture used to take input. Okay, so the input size of this architecture, okay, it was only able to work with the size of 32 cross 32 image. Okay, so this was the image dimension. So at that time, if you see, the image resolution was low. Okay, nowadays we have HD image and 4K image, but at that time we had some like very low resolution image, if you see. Okay, so this input actually used to take this model. Okay, and now let's discuss about this one. Okay, now let's discuss about the architecture. What was the architecture they have developed? Okay. So now let's draw the architecture. Okay. Now let's see like what are the changes they have done. So architecture of LeNet. So as I already told you, input image was okay. So why it's showing like that? Okay. So this was the input image. So it was 32, 32. Okay. So it was our input of the LeNet. Okay. So now what they did, they pass this image to a convolutional layer. Okay. Suppose let's draw the convolution layer here. So it's a convolution 1, CNV 1 layer. Okay. So the number of filter was 6. Okay. And the filter size was 5,5. Okay. Like you are getting like what is 5,5, 3,3. You have learned this filter, basics of filter. Are you getting what I am writing here? Yeah. Okay. So this was like first convolution layer, and in this convolution layer, the filter number of filter was 6, and the filter size was 5,5. Okay, I think so far you have learned 3,3 filter, right? Have you worked with 5x5 filter in your vanilla architecture? No, right? So this is the new term they have introduced. Okay, so, that is why I think you remember here. Actually, I discussed if anyone is creating any architecture, what are the changes they have done? They have changed some, suppose your filter size, or they have done some modification in convolution layer. They have added some extra convolution layer. They added some extra steroid. Then they have came up with the new architecture. Okay, it's nothing but it's just a variation of your vanilla. Okay, suppose just research something. Suppose just create some architecture and observe the output with the ImageNet. If you feel like you are getting a good results apart from like the existing model we are using so far, if you're getting the better output, you can publish your paper also. Okay, so that is how actually research come and different architecture come. See, value would be calculated by your back propagation. Nah, it is like random weights. How I can tell like what is the value of that? Vignesh, I think you got it right. Okay, so now they have introduced another term. Okay, after convolution layer, they have introduced another term called average pooling layer. Average pooling layer. Okay, so it was average pooling layer, and the size of this average pooling layer, okay, pool size was 2 into 2. Okay, and the sprite size was it is like pool size. Okay, pool size, and the sprite size was 2. Okay, I think you got it what I'm explaining, because if you know like average pooling, max pooling, you have learned these things, basic things, right? Pool size, or you can say receptive field size. Okay, so this was size called 2 into 2, and that sprite was 2. Okay, so this is the term they have introduced. Now they pass this output to another convolutional layer. Okay, there was another convolution layer called CNV2 layer. Okay, and this convolutional filter number of filter was 16. Okay, and again they had used 5, 5,5. Okay, like 5 times 5 filter they used. Okay, here, but the first convolution layer, the filter number of filter was 6. The second convolutional, the filter size was the number of filter was 16, and the size remains same. Okay, then again they pass the output the same average pooling layer. Okay, and this size is also same, 2 into 2. This is a pool size, and 2 that is your straight size. Okay, now what they did, they took this output and they apply flatten layer. Okay, so this is my flatten. Okay, so let's name it flatten layer. Okay, so now they took one dense layer. Okay, dense layer. So the first layer was they used around 120 neurons. Okay, 120 neurons they took in the first layer of the fully connected neural network. Okay, and the second layer they took 84 neurons. 84 neurons. Okay, and the last cell, yeah, and at the last cell they took 10 layers. Can you please tell me why they took 10 layers? Here, 10 neuron, 10 output, yes. Okay. Now, we had our output called y hat. This was our output. Okay. And they used something called softmax. Softmax in the last layer. Okay. So now let's connect all the points here. I'm just connecting randomly. Let's say this is the connection we have done. Okay, this thing is nothing but it's your NN, artificial neural network only. Okay. So now why we call it LeNet 5? Okay, I told you we call it LeNet 5. Okay, why call it LeNet 5? Because it has three actually layer. Okay, how it has 3 layer? Because if you see, let me give take another color here. Let's take red. Both of them, okay, this both of them we call it one layer. Okay, so it is layer 1. Layer 1. Then this is layer 2. No, because it has 5 layer. That's why you call it LeNet 5. How it is 5 layer? I'm showing you. See, you can observe here layer 2. Don't consider it's a separate layer. Okay, your convolutional and average pooling together would be 1 layer. Okay, then again convolutional 2 average pooling would be 2 layer. Okay, then you had this is 2 layer you got, and in the NN side, how many layer we took? This is 1 layer. That means layer 3. This is layer 4. Okay, this is 4, and this is the 5 layer. Okay, now I think you got it. How we call it LeNet 5, right? Any confusion till now? Yeah. Okay. So now this was the architecture actually. They have, yeah, filter size is 5, 5,5. Okay, but it's not like 5,5 means it's like LeNet 5. Okay, because 5,5 we'll be using rest of the in our architecture. Okay, it doesn't matter. But LeNet 5, why they have introduced? Because they have introduced 5 layer only. Okay, instead of taking 10 or 15 layers, because 5 layers at that time working good. Yes. Now let's discuss about the image size. Okay, if you are passing your like you can say convolutional or average square layer, so what would be the image size remain? Okay, so now let's discuss it also. Let's take another color here. I'm taking suppose this color orange. Okay, so now this is my input. Okay, if you remember, this was my input. Okay, after passing to my convolutional, okay, this is the convolutional. So I think you remember the, you can say this one. Anybody remember this actually our output size? Okay, so there is something called I think you remember a formula was n plus 2p minus f divided by stride plus 1. Do you remember this formula? Anyone? Okay, so now I'm not going to calculate because I think you have already learned this thing. Okay, I'm not going to calculate. Just let me discuss like what would be the image size. Okay, so your input size was 32,32. Okay, after passing to your convolutional layer, and if you see, if you just calculate, just put the value here, you will get it. So our filter size was what? It was first of all, what was the image size? It's what is 32. Then what was your filter? Filter size, it's 5 cross 5, and the number of filter you had 6. Okay, so now in the first convolution layer, you will get something called 28, 6. Why 6? Because I had 6 filter. Okay, so now it will pass to average pooling layer. Okay, so here you will be getting the average pooling layer. What it will do? Okay, it will just actually divided by 2. Okay, so if you divide it by 2, so what you will get? You will get something called 14, 14, 6. Make sense, everyone? How I'm getting this output? Okay, so now again you will pass to another convolutional layer, this convolution layer. Okay, so what would be the image size? Now it is 14 and I used 5, 5. Okay, so it would be something called 10, 10, 16. Why 16? Because here I number of filter was 16, right? And again I will pass to average pooling layer. Okay, so then what is the output I will be getting? It's 10. If you divide it by 2, you will get 5, 5, 16. Okay, then here this is the final convolutional output you are getting. Okay, now just this is the final convolutional output you are getting. Okay, so now if you multiply together, okay, like 5 cross 5 cross 16, okay, you will get something called 25. You can say times 16, it would be 400. Okay, 400. So 400 parameters you will get here. Okay, 400 parameters you will get here. Now, what is the first layer of input? First layer of dense layer neuron we had. Okay, see, it was 120. Okay, so now just multiply with 120. Okay, then second layer, it would be 120 times 84, because second layer I had 84. Okay, then in the third layer, it should be 84 times 10. Okay, so this is my, this entire thing's my final. Can you understand? Hello, am I audible? Now my voice is fine, everyone. Can you hear me? I don't know, like sometimes I think my internet is not stable, so that's why. Yeah. So this was like our LeNet architecture so far. Okay. Now just tell me, are you able to understand this LeNet architecture or not? It's nothing but you are just adding some extra layer, you are adding some average pooling, you are changing the stride, you are changing the filter size, and you are creating a architecture, you are naming it as LeNet 5. Got it? See, calculation part, it's already done. I think this is the formula. Just put the value here. So image size is like 32. N means your image size. Okay. Then P means what? It's padding. Here I am using any padding, no padding. So that means P would be 0. Okay. And it would be multiply with 2, it would be 0 totally. Then filter size is what? Filter size is 5. Okay. Just put it 5 here. Then stride size was what? Is that I'm using any stride? Yes, I'm using 2 stride. Okay. Just put it here. Then calculate the entire value, you'll get it. Okay, that's how. Just do it like multiple time here. Okay, one by one, you will get this output. Okay, so now we have learned the theory. Yes, that's it. You have created your own architecture, but there is a condition. This architecture should be able to achieve higher accuracy on the ImageNet dataset so far. Okay, you can see the ImageNet benchmark. Okay, every year actually there is a ImageNet competition is going on. Still, like they're developing some model. Okay, and they're trying to get achieve a good accuracy. Okay, I think so far Inception and ResNet is like occupying the highest accuracy, I think. Okay, but if you can achieve like much better, then you can say I mean claim like, yeah, you have done some architecture and you want to publish the paper. Remain same, and not only see, now I will show you, it will be more clear when I will show you the Alexnet architecture, like how you need to, you can add some more here. Okay. Hmm. So now we have cleared with the theory, I think. Now let's code it up. Okay. Now let's launch our like you can say Google Colab. Okay, and let's code it up. Okay, so let me open my, just give me a minute. Hmm. So we'll be following the same architecture. Okay, we'll be following the same, but before that, the thing I'm discussed here. Okay, the thing I'm discussed here, if you open the paper, okay, you will get the same thing. So in the paper, there are many things they have written, but all the thing you are not supposed to consider. Now see the architecture. Now can you understand this architecture? Anyone? What are the things I have discussed? Like input size 32,32. Then they had used something called six you can say filter. Okay, and they got again 28,28. Okay, then again they applied this one, your I mean what I call like average pooling layer. Okay, subsampling. They are calling it subsampling, or you can call it average pooling. Okay. Then again they pass to this one, your convolutional to. Then again they have applied this average pooling layer. Then they applied this one, your flattened layer, and this is the like you can say fully connected neural network they have applied. Okay, that's it. But paper wise they have written some complex thing. That's why I break out this statement and I showed you like in a easy way. Okay, how they have done. Okay, because reading paper is not easy. I think you know. Now everything is clear. Can you please confirm? Can I start with the code? How we can implement this one? Okay, thanks. And if you see they're mentioning this, see pin code. See, okay. What are the things I told you? Okay, this is for this pin code classification, or you can document classification. You can talk about. Okay, this was the first research they have done. Okay, see after giving to the conversion layer how they are getting the feature map and everything they have mentioned here. Yes, yes. I will discuss one theory, one like you can say theory of architecture. Then I can implement with the code. So that's how actually it will be more clear in your mind. Okay. Otherwise, if I discuss another architecture, so it will like that's why. Okay, so let's start our coding. So I will create a folder called FSDS. FSDS. Okay. So inside I will be coding. Okay. So I am sharing this folder access with you. If you want, you can also start coding with me. Yeah, 10 minutes break we will take just after this coding. Okay, after this coding, because we have another architecture to discuss. Okay, because I want to cover two architecture for today. VGG will take time a little bit. Okay, so VGG will be covering tomorrow. VGG, VGG 16, VGG 19. If you see know VGG 16, you will also know VGG 19. Okay, copy and yeah, just confirm me. Can you access this link? So here I will create one Google Colab. You can also start coding with me if you want. Now let's name it LeNet. Okay, LeNet 5. And make sure you are changing your runtime to GPU. And let's connect. Okay. Now, first of all, let's import TensorFlow. We can use any of the framework. If you want, you can use PyTorch also. Okay. You can use MXNet also. You can use TensorFlow also. You can use Keras also. But I think so far you are familiar with Keras. You are compatible with Keras, I guess, right? Here. I mean, you are more comfortable with like which framework, Keras or PyTorch? Hello, guys. Am I audible? Okay. Okay. So let's code it with Keras then. So import TensorFlow as TF. Okay. Then I also need to import Keras from TensorFlow. Import Keras. Then we'll be using MNIST dataset. Okay, MNIST handwritten dataset. So let's import it also from Keras dot dataset import MNIST. Okay. Then I'll also import some layers. Okay, what are the layers we discussed in our theory? Okay, we'll be importing those layers because this layers is already available in your Keras dot layers. Okay, then import. First of all, let's import dense layer. Okay, because we need dense layer. Then I'll be also import flatten layer. Okay, then conv 2D convolutional layer. So 2D. Then I'll be using average pooling. Average pooling 2D. Okay. These are the layer I need to build my entire architecture. Okay. Then I also need something called sequential. Okay, sequential layer. Okay. So from Keras dot model import sequential this one I need. Now let's execute. Okay, it's done perfectly. Now let's load our MNIST dataset. So let's take xtrain. Xtrain, then ytrain, then comma. You have xtest, comma ytest. And let's call our MNIST equal to MNIST. Okay. Then there is a method called load data. Okay. Now execute this. See, it's downloading my data. It's done. Now, before passing this data to my model, I can do some pre-processing to this data. So what I can do, first of all, let's reshape this data. Okay, so performing reshaping. Okay, so let's reshape this data. So first of all, x strength equal to x strength dot reshape. I want to reshape x strength dot shape. I want to take the first value of it, and what is the size? It's 28. I think you remember 28 comma 28. This handwritten digit dimension. Okay, and 1. Okay, why I'm taking 1? Because let me show you what I have done here. See, if I show you my X-Print shape, what is the shape? It's 16. It has 16. You can say 60,000 example, and the shape of is 28 comma 28. Okay, but there was no channel. Okay, because this is a you can say black and white images, right? So there is no channel. Okay, but if you remember, if you are passing this data to your model will always expect one channel. Like you need to pass a channel dimension also. Okay, but here I have no channel. But for RGB, if I taking RGB, so what will happen? But here is no channel I can see. That's why I'm adding a channel 1. Okay, channel 1, that means no channel. No channel means channel 1. Okay, I think you got it, what I'm doing. And this thing, I had 60,000 example. That's why I'm taking 60,000 here. If you do the shape, and if you take the first example of it, so it would be 60,000 only. Clear? What I'm doing? Just confirm me in the chat. Okay. So similar wise, yes, you can use NumPy also. It's fine. There are many way, but I feel like this is a like easy way, and people can also understand. Okay. So then let's do it for test also. X test. So I'll calling my X test dot reshape. Okay. So here, what I need to do, I need to pass my X test dot shape. I'll be taking the first example, and I'll copy the same because it will remain same for my test also. Okay. So this was like our performing reshaping operation. Okay. So now let's execute the cell. And now if I show you my extend shape, there is a little bit difference you will see. I have done nothing. I have just added this one dimension. Okay. Just for my input of my model. Okay. That's it. Now, the second pre-processing I want to do the normalize my data. Normalization. Normalization. Can anyone tell like why you need to do a normalization here? If I don't do normalization, what will happen? Just basics you have learned till now. Yes. Okay. Now, why I'm doing the normalization? Let's see. Because if you see, suppose this is my image. Okay, this is my image. Image is nothing but it's a pixel. Okay, it's a pixel. Suppose somewhere it would be 0, somewhere it would be 1, somewhere it would be 55, minus 55. Okay, then again it would be 100. Okay, then again it would be 255, 0, 1. So you can see there are many variation of the number. Okay, but this number is like somewhere you can see 0 is like very less than 55. Okay, then again minus 55 is very less than 55. Then again 100 is very smaller than this 255. So there are many variation of the number. But if I can like make this number, okay, this range, okay, so it would be make our model to converse faster. Okay. Okay. So that is why we'll be doing this normalization. Okay. And we'll be using something called min-max normalization. Okay, min-max normalization, what? It's nothing but you are dividing your entire pixel by 255. Okay, that's it. So let's write it. Extend, comma, extend divided by 255. That's it. Okay, this will give you the range between. No, it should be -1 to 1. Why? Because no, it's fine. Yeah, 0 to 1, 0 to 1. Sorry. Yeah, 0 to 1. It's correct. Okay. So now let's define another my test also. X test. Okay. Now let's divide by 255. Okay, 255. So now let's execute this one also. So I've done my normalization also. Okay, it's fine. So now if I show you my y trend, suppose I'm taking the first value of y trend. Let's see what is there. It's 5. It's only 5. Okay. But to train your model, okay, you can do one thing. Like if you want, you can do one thing, because if you see this range is also will vary. Suppose it's a digit, like it would be 1, 2, 3, 4, 5, 6, 7, 8, like that. Okay. So what we can do, we can apply the one-hot encoding to convert this 5 to something called you can say 1, 10. Okay, 1, 10. So what will happen? It will you can say apply the one-hot coding, and it will give me some results like that 0, 0, 0, suppose if there is a 5 like 5 is present, it would be 1, then again it would be 0. Okay, 0, 0, 0. Okay, so it would be till 10. Okay, it should be 10 value. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Okay, so that is what I need to convert. Okay, because my model would be learning better way if I'm passing that way. Okay, so let's do it also. So let's apply one-hot encoding. So yeah, one-hot encoding for output column. Okay, so let's do it. So let's call y trend. Okay, y trend. There is something called under utils dot to category. Okay, there is some like you can say method called to categorical. Now pass your y trend just here. Okay, and just mention the output dimension you want. Okay, it's 10. Okay, because I had 10 examples, right? So that's why I'm mentioning this. No. It's like a little bit different. See, if you can execute like from your side, you will get the idea. Okay. And the way you have done till now, you can also do it. But what I feel like this way is like more, good. Okay. Learning better way. Why 10? Because how many number you have output? 0 to 9, right? And one-hot encoding means what? Okay. Just if you want to represent the 5, okay, in a number, how you can do that? Got it? 0, 0, 0, 0. Wherever it's 5, it will give 1. Then again 0, 0, 0. Got it? The same thing you do in the machine learning. Here, I'm doing here also. So now, let's copy the same thing. It's a like, you can say formula. Okay. It's a min-max formula. It's a min-max scaling we're doing. Min-max. That's it. Okay, you can search the min-max formula, you will get it. They're also dividing by 255. Okay. To get the range to 0, 0 to 1. Okay. So now let's do it for our test also. Test, okay. So it's done. Now let's execute the code. Okay, now if I show my train, the first example right now. Okay, now you are getting the representation 5 like that. Now you got it why I did the one-hot coding. Okay. Now instead of just consider 5, 6, 9 like that, it can learn better way because now it can represent. Okay, it can represent in a higher dimension. Okay, see, this is the 5 here. It is representing, and all rest of the thing are 0 because 5 is here on. Okay, so now let's create my architecture because see, data is not our main concern. I just want to show you the architecture how I can create. Okay, the main thing is like architecture creation. Data you can prepare it's your own way. Okay, but I just want to show you like these are the things you can do. Okay, now let's make our architecture. So model architecture. Okay. So now how I can create my architecture. First of all, you need to call your sequential because it would be sequence by sequence. Okay, it's not like skip connection we are doing. Sequential. I think sequential spelling is correct here. Sequential. Okay. Now model dot add. First of all, which layer I need to add? Can anyone recall? Just go to this architecture. So our first layer was convolutional layer. Okay. And what was the number of filter? It was 6 and the filter size was 5,5, right? There was no padding. Got it? Yeah. Input layer would be by default. It would be by default. Okay. Input you are not supposed to take. If you are passing in the sequential layer, input layer automatically will consider. Okay. And in input layer, I'll mention also, like if you see, I'll mention, and there is a like one issue I will show you also. If you are using MNIST, so there should be one issue. Okay, I'll show you also. Then this was like thing. Okay, now let's implement this one. So my first layer was convolution. So I'll just call my on 2D. Okay, inside a number of filter I had 6. Kernel underscore size. It was 5,5. Okay, 5,5. And can anyone tell like if I give padding is equal to valid, so what does it mean? I think you have learned padding is equal to valid. Do you know what is the difference between valid and same? Yes, no padding. Okay. Okay, no padding. But if you are mentioning same, that means you want padding, right? Okay, because our first, if you see there was no padding, so I'm taking as valid. Okay, I'm taking as valid. That's it. Now there is one thing I haven't told you yet. Okay, because I just wanted to show you here. If you just read the paper, okay, if you just read this paper, where is the paper? Yeah, Likan. If you just read the paper, they have clearly mentioned activation function wise in the LeNet architecture, they use something called tanh. Okay, tanh. So this was the first activation function they used. Okay, in there. Nowadays, if you see any architecture, you won't be using tanh. You'll be always using ReLU. Okay, because research proved that ReLU is a non-linear activation function and it will give you better outputs. Okay, instead of taking tanh, sigma, and this one. But at the time they used tanh activation function. Okay, so that was the another difference. Okay, in this linear architecture. So after tanh, now let's define my input size. Okay, input size. Okay, because input shape I need to mention input shape. So what was the input shape? If you remember, it was 32, 32. Okay, but there would be a issue. Okay, I will tell you when would be a issue. Let's execute the code first of all. Okay, 32, 32, 1. Okay, so this was my input. Now let's give another. Now let's see our second layer. What was the second layer? It was, yeah. Second layer means suppose layer 1 we haven't completed it because layer 1 will like you can say consist of two layer, like convolution 1 and average pooling. Combining this two layer, we'll call it layer 1. Okay, so now we need to again add one layer called average pooling. Okay, now let's add it also. So now I will do model dot add, and here I need to call my average pooling 2D, and inside I need to pass my pool size. I think you remember what was the pool size. It was 2,2, right? Pool size, it was something called 2,2. Okay, 2,2. And what was the stride size? First line itself mean? No, see, you are adding layer by layer. See, just consider as a layer by layer. The same architecture we have done here, layer by layer. Okay. So stride, STRI, stride. Okay, stride. It was 2. Then was there any padding? There was no padding. Okay, so there was no padding. Now give our padding as valid. Okay, padding is valid. And yeah, it's almost done. If you see, my first layer is done. Okay, we have added convolutional layer and average pooling also, and pooling size was 2,2. Just a minute there. I got a call. Yeah, guys, am I audible? Actually, I got a call. Actually, sorry for the disturbance. Yeah. Okay, so sorry. Actually, it would be strides, I think. Okay, thanks. Good observation. Stride. Okay. So now my this first layer is complete. Okay, first layer is complete. Now let's focus on the second layer. Okay, now let's focus on the second layer. So what was the second layer? I think you remember. Again, I need to take one convolutional layer. It has 16 filters, and the filter size was 5,5. Okay. Then again, it has average pooling the same average pooling I can take. Okay. Now let's build this also. Now I will do model. Instead of creating from scratch, I can copy. Okay. Now here I need to mention 16 because 16 filter was there, and filter size is like 5,5. It's fine. No padding, valid. Activation function I need to take 10h, and input I don't have to define because input can be only defined one time. Okay. Now the same thing I will copy and paste here because this will remain same. Okay, for my second layer. So it is my first layer, it is my second layer. We have done. Now let's see what is left. Now I need to take a flattened layer here. If you see, now let's take a flattened layer here. So model. Neural network. So the first neuron will contain, if you see, there were three layers. Okay, 1, 2, 3 we have taken. So the first one will contain 120 neurons. Okay, now let's build it. So I'll define model dot add, model dot add. So dense. Okay, dense. Inside this I need to mention 120 neuron I want, and the activation function 10h. Okay, that's it. Now again, there were three dense layer. The second dense layer will contain 84 neuron. You see, 84 neuron. Okay, so now let's give 84 instead of 120. 84. Okay, and the activation function is 10h. Okay, now the third neuron, it will contain 10, because my output is 10. Okay, and here what activation function I need to use? Can anybody tell me? This is my last layer. Softmax. Yes, right. Softmax. Okay, Softmax. And if you see, they have also used Softmax. Okay, in there. Now, if I print my model summary, model.summary. Okay. Now let's execute. If everything is fine, it will give me the summary. Okay. Now see, it's giving the summary, and you can see all the parameters. Okay. Your average pulling won't have any parameter, because average pulling will be only reduce the pixel size. Okay. You don't have any parameters. Okay. So only parameters will contain your convolutional layer, your dense layer. Okay. That's it. And now total parameters, if you see in LeNet, it's 61,706 parameters. Okay. These are the trainable parameter you have. This was our first architecture of the CNN. Okay. And using this architecture, this actually idea, now they have came up with a mini architecture. What are the architecture I showed you? Okay. But the concept that came from, okay, Jan LeCun first of all introduced these concepts. Okay. That's how we can create any kinds of CNN architecture. Okay. So now let's test. Okay, now let's train this architecture. Okay, now let's test. First of all, what I need to do, I need to do the compile of my model. I think you know, if you're using Keras, so you need to do the compilation. Compile. So loss function, I'll be using categorical cross entropy. So I'll call it on Keras dot matrix. Okay, and called categorical cross entropy. Okay, this loss I'll be using because this is the categorical problem statement. Okay, now optimizer I will be using. I think you know Adam, right? Adam, you have heard of, and Adam will work mostly fine in every situation. Because why Adam is fine? I think you learn the theory. Okay, because in Adam actually it will use your momentum and everything, right? It would be first conversion, right? Instead of using HGD and Y. Sparse actually I won't be using, because sparse you can also use, but categorical cross entropy most of the time you will be using whenever you're doing the image classification. Okay, got it. You can use it. There are many variation of the loss function. I think Sunny sir has also discussed like what is the advantages of it, right? See, dead relu concept will come later. This was like a basics architecture. It was first architecture. Don't expect dead relu right now, right? Relu I haven't used here. Okay, it would be introduced inside your ResNet inception, this one. Okay. Okay, don't consider the parameter, the loss function optimizer I'm using. Just consider the architecture we have developed. You can do it. This is the hyperparameter. You can like change it anytime. Okay, there is no rule. You need to use this one I'm using. Okay, just for demonstration purpose, just for quick purpose I'm using. Okay, so Keras dot optimizers. Okay, I'll be using Adam. Okay, Adam. Let's take the default learning rate. I won't be changing anything. And metrics. Okay, metrics I will be using accuracy metrics because this is the classification. Accuracy metrics. Now let's compile my model. Okay, compilation is done. Now let's fit my data. So model dot fit. I will pass my extreme. Again, I will pass my trend. Okay. Now I need to define the batch size. Okay, batch size. Let's take 128 and epochs. Just doing. Epochs. I'll be defining 10 epochs. That's 10. And verbose. Verbose, I want to see the logs in my output, so that's why I will keep verbose is equal to 1. And validation data. Keeping my what you have X test and you have Y test. Okay, That's it. Now let's execute and see it is able to train or not. Okay. Yeah. So that is the error I just wanted to show you. Now, can anybody tell me what is the problem? Why I'm getting this error? It's telling input 0 of layer sequential is compatible with the layer expected shape 32 comma 1, but found shape 28 comma 1. No. Yes. So this is the error I just wanted to show you, because if you see my MNIST dimension is what? 28 comma 28. But LeNet expect 32 comma 32, right? Now either what you can do, either you can use image the shape of like you can say 32 comma 32. Either you can just mention the default shape you have. Okay, just change it to 28. Okay, suppose you don't have 32 image right now, but you want to do the experiment. Just mention 28. Okay, here. Okay, so you are not supposed to like change anything. Now if I execute it again, and now again compile the model. Now let's start training. Okay, now you will see there won't be any output. Okay, this is just for demonstration purpose, but whenever you are creating actual model, at that time you will be using the data, you will be doing the reshaping operation with respect to your model size and all. Okay, but here I am not doing. I just wanted to show you the architecture. That's it. Okay, and I'm using the default image size I'm using. Just mention it here. Okay, that's it. Now if you see it's training and see accuracy is like pretty good. It's giving because it was only for the handwritten classification and all. Okay, that's why it will work fine here. Okay. No. It said LeNet. It's LeNet only. It's LeNet. See, input size doesn't matter. You can change it, no issue. Okay. But the architecture we have built, that should remain same. Suppose you are changing this kernel size like 3,3 instead of 5. At that time, it won't be LeNet. Got it? But they have mentioned input size should be 32 because at that time 32 was the highest resolution of our images, right? Yes, and any input it can, but if you are increasing the input, suppose you are giving suppose SD images you are giving, suppose 255 dimension you are giving, at that time you will see like very bad accuracy will be getting because that image was like very big and you're using some 2 layers only. Okay, some small filter you are using, so it would be able to learn perfectly. But here 28 and 32 almost same, the pixel is almost same, right? So that's why it is able to learn in a very better way. Yes, if you are increasing above 32, at that time your LeNet model will fail. It won't be able to learn. That's why we have came up with other architecture. Nah, in the next one, I will introduce another architecture. Okay, it will take input as 227, 227 input. Got it? What is 6 represent? Which line? This 6. Ashok. This is the filter, number of filter I'm using. I think you should be familiar with these concepts. These are the already covered, I think, basics. Okay, I discussed now here, if you see, number of filters, 6. The first layer they took. Okay, even if you see their paper, see, 6. Okay. So now see, this is my final accuracy. Now let's calculate the accuracy also. So score model dot evaluate. Okay, I'll pass my X data. Sorry, X test. Okay. Now if I print my test class, test class. So it would be something called score. The first first value of my test loss and my accuracy, test accuracy, the first value of it. Okay. Now see, this is my accuracy, and it is working pretty good, like with this one. Okay. And if you just apply some kinds of pre-processing also in your data, it will give you some good results also. See, your custom, how to train your custom image, that would be also teachers. Okay, no issue. But this main agenda of this class is to introduce the LeNet architecture. I mean, CNN architecture. Okay, that can be done. There are many projects you have. Okay, don't worry about that. We'll be using our own custom image, and I will also show like how to prepare this data set, how to resizing. Okay, everything will be shown. No issue. Don't worry. As of now, the theory you have learned, can you able to implement with the code or not? Just tell me, right? Make sense everything? Everything I showed you in live. Okay, by seeing the architecture, you can develop the code. Clear? To the image segmentation, then mask RCN and need to run. That concept will come later on. Don't focus on right now. Okay. So this was all about our LeNet, LeNet 5. How do you know means see this is the architecture? Just open up the paper, see the architecture, relate with the code. Everything is fine or not. That's how it's LeNet architecture. You have everything. Code, you have paper, you have even my this, you can say notes. Okay. Now by seeing the architecture, by seeing the code, can you tell me like is it a LeNet architecture or other? Deepak, you are getting why this error? Just refer my code. Everything is fine. Okay. I think you can access my notebook. Refresh and use. Okay. Yes, yes. So let's take break. 10 minutes of break. 10 minutes is fine, everyone. Let's take water break of 10 minutes. Those who are getting error, actually just refer my notebook. Okay. Don't do anything extra. Okay. I have done. No, LeNet has actually just two convolutional layer. Convolution 1, convolution 2, and 2 average pooling. Okay. And 3 NN. Okay, those who ever getting error, just keep it. Okay, we'll see at the last of the class. Okay, we'll be taking doubts, then I will see that. Yes, no, flatten is not a convolutional. Flatten is like just you are getting the tensor, you want to do the flatten, that's it. Flatten means what? Suppose here you are getting something called suppose 4-dimensional array, and you want to convert it to 1-dimensional. Okay, suppose this is the 1-dimensional array you want to convert. Okay, that's why we do flattening operation. Okay. All number will remain in a one line at a time. Okay, now let's take 10 minutes of break. I think Is everyone back? Okay. Okay, now let's start with our second architecture, something called Alexnet. Okay. Now let's see the difference between this Alexnet and LeNet. Okay, what are the changes they have done? Okay, I'm sharing my screen. Yeah. Now we'll be discussing something called Alexnet. Okay, Alexnet. So Alexnet is nothing but Alexnet was designed by a researcher called Jeffrey Hinton. Do you know Jeffrey Hinton, who is the creation of backpropagation algorithm? My like you can say board is visible to all of you. Can you see what I'm writing, or should I increase the thickness? Okay. Okay, I can increase the thickness. Okay, Jeffrey Hinton. Okay, Jeffrey Hinton. And this architecture was winner of the 2012 Imagenet competition. Okay, and there were another researcher. He has contributed. He was the student of Jeffrey Hinton. His name is Alex. Is Tishivsky, or I don't know like how to spelling. Can you spell it or not? So let's call it Alex. Okay, Alex. So he was the student. Okay, he was the student. Okay, of Jeffrey Hinton. So they actually contributed to this paper, and it was the winner of the like competition of 2012. Okay, ImageNet competition winner. Okay, so now let's see. So this Alexnet, if you see our LeNet, okay, the input size was 32,32. Okay, but they have introduced some bigger resolution image. Okay, and the size was 227 times 227. Okay, so this is the image input size, okay, of this Alexnet. And what are the new things they have, you can say, this LeNet paper, sorry, Alexnet paper. So this is the Alexnet paper, and if I show you, okay, so this is the Alexnet paper. Okay, so ImageNet classification with deep convolutional neural network, and Jeffrey Hinton and Alex, and there is another author. Okay, University of Toronto. They had this published, and there is architecture if you see, and this is the our Alexnet architecture. But if you see, it's like a little bit hard to understand. Okay, from this paper, because as you can see, it's not like very I mean clean to understand. So now let's break down this one. Okay, let's make it as clear so that we can understand what is happening. Okay, in this architecture. So let me open my board again. Okay, now let's see the architecture. So first of all, let's take our input image. So the image size was 227, 27. Okay, it was my input. Okay, it was my input. Now they created something called convolutional layer. Okay, so convolutional layer. Suppose this is the convolutional layer. Okay, and in that convolutional layer, the kernel was okay. Here they took kernel. That means your filter. They introduced first of all 96 filter. Okay, 96 filter they took, and the filter size was 11 cross 11. Okay, this was the filter size, and they took another thing called stride. Stride is equal to 4. Okay, stride is equal to 4. They took, and yes, this is like your first convolutional layer. Okay, so now if you remember the formula, let's write the formula here. N plus 2p minus f divided by s plus 1. So this is the formula we'll be always using to calculate this one. Okay, so now let's calculate. Okay, I mean in your next layer, okay, what should be the input shape? Okay, so this was like your first convolutional layer. So now if you just pass the number to a formula, so first of all it was n, that means your input. So input was like 227, then minus 11. So 11 is what? If you see, there was no padding. Okay, that's why padding would be 0. Okay, this term would be 0. That's why I'm not adding padding. Filter. Okay, filter size is 11. Okay, so that's why I would be taking 11. And your stride is what? Stride is 4. So that means divided by 4 and plus 1. Okay, so now if you calculate that, so their input would be something called 5, comma. So this is the dimension. Okay, your image dimension will reduce this thing. Okay, now you got it like what I did here. Anyone just clear this thing? After taking the input, whenever you pass to your first convolutional layer, you got the output this one, 55, 55. You got it using this formula only. That's it. Okay. Now this input will go to another layer called max pooling. Okay. Yeah, this is your max pooling. Okay, max pooling. So whenever you're passing this to your max pooling, so what would be the calculation? Let's see. Okay, now max pooling calculation, let's see what would be. So max pooling, what was your input size? It was 55. Okay, 55. And in that max pooling, they have taken pool size as 3 cross 3. Okay, 3 cross 3. And stride was 2. Okay, stride was 2. So this is the thing they took. Now, if you just put it to your formula, so now 55 minus, because no padding, it would be 0. Your filter size was what? It was 3. Okay. Now divided by your what? Okay. So here if you see, okay, just wait. Yeah, fine. Yeah, it's fine, I think. I think stride, it's fine. Okay. So if you just put and stride, there was 2 stride. Okay, there was 2 stride. Okay, and it was plus. Okay. Now if you just calculate, so what would be the input of this? I mean your output of this max pooling layer? It would be something called 27, 27. Okay. So this would be the output. Now this output again, what they did? Again they passed to another convolutional layer. Okay, another convolutional layer. CNV2. Okay, convolutional layer. And this convolutional layer, it has 256 filter. Okay, 256 filter, and filter size was 5 times 5. Okay, this was the filter size. And here if you see the padding, okay, then they have added the padding some. Okay, padding they took 2. Okay, padding they took 2 here, and there was no stride. So now let's calculate for this convolutional. Okay, now let's calculate here. So now what would be the output of this convolutional? Okay, so now the input was like 27. Okay, and if you see, there is a formula, there was a padding is equal to 2. So 2 times 2. Okay, 2 times 2, and stride, there was no stride, I think. Okay, there was no stride, so it would be 0. So I won't be giving anything here, and plus 1. Okay, plus 1. So now if you just calculate again, what you will get? You will get 27. Okay, so now this output would be something called 27, 27. Okay, so now again, sorry. Okay, again, what you need to do? Again, you will pass to your max pooling layer. Okay, yeah, max. Yeah, this thing will remain same, na? Like your 256. This will remain same. Okay, this will remain same for sure. But I'm talking the output. Okay, output of this one, like because you are adding padding. You are adding padding means the input side will remain same. The input it got from the like previous layer. Got it? Anyone? Just see step by step. See, it the output was 27. Here I use padding is equal to 2. Then I calculated this value. Again, I got 27. Okay, for the next output. Okay, and this filter size will remain same, 256. Yes, and filter will remain same. Like it would be 256 only. Okay. Now let's pass it to our again max pooling layer. So I will call max pooling. Okay, max pooling. So here now the pool size is 3 into 3, and stride is equal to 2. Okay, they took. And now if you do the again calculation here using the same formula, so your input was 27 minus there is no padding, so it would be 0. Our filter size is 3. Okay, now stride is 2 by 2 plus 1. Okay, plus 1. Now if you do the calculation, what is the value you will get? You will get 13. Okay, so the output would be something called 30 13, 13. Okay, 13, 13 you will get. So now what you need to do, 13, 13 you got here. Okay, so again you need to pass this thing. Sorry, you need to pass this thing to another convolutional layer. Okay, so this is another convolutional layer. Convolution layer. Okay, so now here they used around, you can say, 384 kernels. Okay, that means filter, and the filter size was 3 into 3. Okay, now if you see, one thing you can observe here, the more you are passing to your convolutional layer, your filter size is increasing. Suppose the first filter, if you see, it was 96. Okay, then whenever I took another convolutional layer, okay, the filter was 256. Then again, after passing to the max pooling, again I pass to another convolutional layer, the filter size is 384. Okay, it's increasing. Okay, so now what would be the output of it? So now let's see. It was 384 kernels. That means filter, and the filter size was 3 cross 3. Okay, 3 cross 3. There is no padding is equal to padding. Okay, padding is equal to 1 means there is no padding. Okay, there is 0 padding. Okay, padding is 0 padding. Now if you just calculate here also, so what you will get, the output was 13. Your previous example it was 13 minus you have padding is equal to 1, so 2 comma 1. No, here they have introduced something called padding. Okay, padding is equal to 1. Okay, then again, what is your kernel size? It's 3. Okay, then you have a sprite. No, there is no sprite. Okay, so I'll just give plus something called 13. Okay, 13. So this would be 13 comma 13. Okay, again. Now again, what you need to do, again you will pass this value to another convolutional layer. Okay, another convolutional layer. Another convolutional layer. Okay, so this convolutional layer, it will have 384 you can say filter again, and the kernel size would be 3 cross 3. Okay, 3 cross 3. Pad is equal to 1. Max pooling, the average pooling, like it's like max pooling. Max pooling means it will divide it by 2. Okay, it will reduce by 2. Have you learned of pooling, like average pooling, max pooling? This thing I think you have learned. Pooling means what? It will only consider those highest pixel value from your entire pixel. Suppose this is the image. Okay, during convolution, what happened? Your filter will look for some of the edges, right, from your images. So it will only consider the highest pixel value. Okay, max pooling. Okay, so that's why max pooling layer, because in our LeNet architecture we are using average pooling, but here we are using something called max pooling. Okay, see, now they have changed this architecture slightly different. They have introduced some new terms and they have made this architecture. 11 cross 11 kernel means this is your 5 cross 5 kernel. So if you see, it would be 5 here. 1, 2, 3, 4, 5. Okay, 5. 1, 2, 3, 4, 5. Okay, this is the 5 cross 5. Okay, 11 cross 11 means your row should be 11. Row should be 11. Column also should be 11. This is a big filter. Got it? Because your image size is also big. If you see 227 pixel you are getting, right? That's why you are increasing your the filter size also. Got it? No pooling. It's directly passed to again another convolutional. Okay. So now here, what would be the output? If you just again calculate the same value, okay, here 13 was there, the like previous output. Okay, so here you will here I'm using padding 1. Okay, again you will get something called 13 comma 13. Okay, 13 comma 13. Then again it would be passed to something called max pooling. Max pool. Okay, max pool. Then max pool, here they introduced max pool. Your pooling size is 3 cross 3. Okay, then your stride is equal to 2. Stride is equal to 2. Let's zoom a little bit. Okay, stride is equal to 2. They mentioned this one. So stride is equal to 2. And what would be the output? The output would be something called 6 comma 6. Okay, so this is the output. Okay, this is the final output, and this output will pass to a flattened layer. Okay, this is the flattened layer, and this flattened layer will pass to a FC layer. Okay, fully connected layer. Suppose there are some neuron, and it will contain. Okay, it will contain the neuron 4096 neuron. Okay, the first layer, and the second layer again it will contain 4096 neuron. Okay, and the last layer it was 1000 neuron. Why 1000 layer? Because they are using Imagenet. Okay, Imagenet. And if you know, Imagenet has 1000 class. So this is the final output they are getting. Okay. High stride means you are skipping more pixels. Suppose this is the image. Stride means what? Suppose this is the kernel. This is the kernel. Okay, this is the kernel. Sorry. This is the kernel. And stride means what? Suppose you are taking stride as 2. That means it will just jump 1 pixel. Okay, then it will give here. But if you are increasing the like stride, so what will happen? It will jump like it was there. If you increase the pixel, it won't consider this pixel again. It will come here. Okay, so that's why you're losing some information. So don't keep high stride. You can see stride. Okay, always take low stride. Okay. Now, what are the things I have written here? I just want to show you like in a better way. So let me download a picture first of all. Okay, let me show you a picture. I think you will get better understanding. Just wait. Alexnet. So I got a picture. Yeah, I think this picture is visible, all of you. Right? So see, what are the things I discussed? Okay, the same thing is also here. Okay. First of all, you have your image. Okay, you have your like 227 image. Then you took a convolutional layer. You passed your, you can say, yeah, photo. Okay. Then this is the calculation is going on. The same formula we are using, right? Then after that, again you are passing to the max pooling layer. After max pooling layer, again you are passing to the convolutional layer. Okay. Then again you are passing to the max pooling layer, and this max pooling layer again passing to the convolution layer, again convolutional layer, again convolution layer, again max pooling layer. Okay. Then once it is done, you are doing it as a flattening, and you are passing to your fully connected neural network. Again, your fully connected neural network. Okay. Then this last, this is your output. Clear? Or any questions you have? You can take a screenshot of this picture, okay, if you want to remember, because this is a little bit longer, okay, this is a longer architecture, okay, so that's why you are not supposed to remember. Whenever you forget, just open this up and you will get it. But concept wise, I think it should be clear in your mind. Dotted means this is the filter, 11x11 filter they are using. So they are just like drawn as a picture here, okay. See why there should be any stride, because this is the architecture they have made. They didn't give any stride here. Okay, that's how I told you, na. If you are changing stride, if you are suppose removing stride, that's how you are able to create a new architecture. Okay, I'm sharing these images with you. Okay, so these kinds of modification they did. Now I think you can relate with your previous like architecture. What are the new terms they have added here? They have added. So now let's write what are the new terms they have added. Okay, new terms. Okay. New terms. So new terms wise they had added. The first one they have added 11x11 filter. Okay, 11x11 filter, and also added 5x5 filter. Okay. Then the second thing they have added, instead of average pooling. Okay. And the some more thing they have added, I will discuss whenever I will be making it. Okay, so they have added what? They have added something called dropout. Okay, dropout layer they have added just for removing the overfitting condition. And they have also added something called normalization. Normalization. Okay, batch normalization you can consider. Okay, batch normalization. But they have used something called local response normalization. Okay, local response normalization. Okay, it's like kinda batch normalization only. Okay. So number of filter, if you see here, number of filter they have increased also. So here you can again consider filter size has been increased. Okay. Okay, increased. So now I think this thing is clear in your mind. Okay, if you are getting any kinds of new architecture, what are the things they have done? Okay, in this architecture, it's just the same like theory only we have learned in our vanilla, but they are changing this as parameter only. That's it. Now I think it should be clear, all of you. Yes. So now the convolutional layer, if you see here, let me do the annotate. Okay. So first of all, after image, you are passing to a convolutional layer. Okay. See, convolutional layer, then max pooling, P. Okay. Then again, you are passing convolutional layer, C. Just remember this pattern. Then again, you are passing to a pooling layer, P. Then again, you are passing to a convolutional layer, C. Again, you are passing to convolutional layer, C. Okay. Then again, you are passing to convolutional layer. Again, you are passing to convolutional layer. Again, you are passing to pooling layer. Okay. And then you are passing to dense layer. That's it. That means C, P, C, P, C, 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 P, D. Okay. Just remember this one. Okay. You will get the entire workflow of your architecture. Yes, overlapping. This overlapping max pool means this is the same thing we are discussing, the max pooling. Okay, but they have named it in a different way, because all this paper, I think if you see research paper, always name will come with a new terms. Okay, but the same thing, max pooling only they are using. It is clear now, everyone? Just confirm me. Let's start coding. Hello. Okay, and they introduce another thing called this one. Your instead of taking lower, you can say layer. Okay, the same layer they took, and then they took y hat. That means output layer. Okay, 1000 submits. Okay, but for your case, you will just drop this layer, and you will replace with your. Suppose you have 10 example. Okay, 10 example. Instead of taking 1000, you need to take 10 neuron at the output. Yes, I will tell you. I will also code it up using a new data. Okay. Custom data, we have a session, don't worry. Okay. We'll download image and we'll be training and all. Okay. The same things you will be just like building. Okay. But your data preparation would be like, it would be different. Okay. Because data is what you can prepare. Okay. How you can prepare, it's up to you. You can do augmentation, you can do anything. Okay. This thing actually will remain same. Okay. This thing always you need to remember. Okay. If you have now understanding on Alexnet and this LeNet architecture, the rest of the thing you will very easily get it. But there are some slightly differences resonate because they are using some residual connection. That means skip connection. Okay. It is a little bit difficult to understand, but we'll also explain this one. Don't worry. Okay. See, we don't use LeNet Alexnet. Okay, because this is for understanding only. If you see the Keras application, just wait. Let me clear the board. Yeah. If you see the Keras application, what are the sorry. What are the architecture you can see you use that only. Okay, because this has been proved by like it will work fine. Okay, we don't have to use Alexnet and LeNet. But just for learning purpose, just for experiment purpose, you can use because we can implement this to I mean you can say architecture, okay, in a very easy because these are a little small architecture. But if you see Inception, Resonate, we won't be able to draw it. Okay, it is like very big. Okay, the layer number of layer is like very big. Okay, so that's why to understand these concepts, what is happening inside Resonate, what is happening inside Inception. Okay, so we use this thing LeNet and like you can say Alexnet to understand because these were some first I mean created architecture. Okay, and rest of the architecture has been created based on that only. The idea came from here only. Okay, this thing. Yes, I am pasting the image. Copy image. Yes, just for your reference, you can take it. Okay, this is the architecture. Now let's convert it to code. Okay. Hmm. See, in real time, you can't decide which architecture you used. Okay, it depends upon your data. Suppose you have like you can say 5 class. Okay, and this class is like very I mean very easy, like not much complex. Suppose you have flower data set. Okay, just use a small model first of all. Let's see the output. Observe if it is not giving, just take bigger model. Okay, that's why you need to do some multiple experiment, then you will get the answer. Okay. Questions they will ask like if I talk about specifically in classification, so they may ask you like what is the use of this max pooling layer? Okay, what is the use of this convolutional layer? How filter is extracting the features? Okay, these are the thing, but they won't be asking the entire architecture. You are not supposed to remember. Okay, just try to understand the concepts, what is going on. That's it. Dropout will be using in architecture. You are not supposed to mention dropout because architecture main thing is like your layer. Okay, dropout you can use either you are not it's not like you need to use the dropout. Okay, it's up to you. You can use, otherwise you can't use. Okay, suppose if your data set is too simple. Okay, so what will happen, your model might get overfitted, right? At that time you can add some dropout. This is the red paper. They've introduced some of the new terms. If you see what they have added something called data augmentation. They told you to get the good accuracy, just add data augmentation also. If you are augmenting your data, you will get good accuracy. Okay, reducing the overfitting also. If you see, and they have also added dropout. Okay, introduce the dropout in this architecture. Then they have mentioned what is the use of dropout. Then they have also mentioned something called here. If you see architecture dataset, ReLU, see there in our previous architecture we used something called TANH, but they have used ReLU here. Okay. Then training on multi GPU. They have also introduced multi GPU training in that. Local response normalization, that thing I told you. That means you can also consider batch normalization. Okay. This is the formula. Overlapping pooling. Overlapping pooling means max pooling. Okay. The same thing. Then I already discussed data augmentation. You can see these are some optional. You can add data augmentation, dropout. You can add. It's optional. Yes, you can take architecture reference. Okay, just open the architecture reference. See, I will implement. I will implement using this architecture only. Okay, but dropout you can add. Either you don't. I mean, you can't add. Okay, it's up to you. Okay, there is no restriction. You can add dropout. Okay, but this architecture flow would be same. Okay, then you can call it as a Alexnet. Okay, so now let's implement this one as a code. So let's open my. Here I'll be creating another Google Colab. Local response normalization, it's nothing but it's kind of, you can say, batch normalization only. I think Sarah has taught you in the class. Okay, but they have came up with a new equation here. If you see, this is the equation of local. Okay, do you remember the batch normalization equation? Anyone? Okay, it's replaced with this equation. You will get something called local response normalization. Okay, so you can see they have also mentioned either you can also see batch normalization. You can also mention here. Okay, no issue. Okay, but at the end you need to give a normalized layer so that your pixel would be normalized. Okay, whenever it is going for convolution. Kavi, I think you got it. So let's name it Alexnet. Okay, so I'm not going to code it from scratch because this is a little bit bigger. It will take time. So I already coded. So I'll just explain. Okay, so first of all, let's import some of the library and make sure you are selecting GPU. Connect. Okay, the same thing you need dense activation dropout. See here I am using dropout, flatten, and max pooling instead of average pooling. See, just compare with that. Compare with that only. That's it. Okay, nothing is there. Now let's execute. So here I will install one thing called tflearn. Okay, why I'm installing? Because I want some data. Okay, so I will be using flower data here. So from tflearn I can get flower data. So this is a package. Okay, TensorFlow learn. So inside you will get a data. Okay, so now if you want to get the data, so this is the code. You can use any data. Just for demonstration purpose I'm showing. Don't consider the data. Don't consider the, you can say, I mean the pre-processing I'm doing here. Just consider the architecture how I'm building. That's it. Okay, because data preparation, data loading you will be doing. Okay, in your day-to-day, like, okay, it's like it will remain same. But try to understand the concepts, the theory you have learned. Okay, yeah, collab link. I think I shared everything. FSDS get link. There are 2 collab file. If you open this link, you will get. Just open the Alexnet one. Okay, can you access? Just tell me, Vignesh. Okay, so now from tflearn dataset, there is a data called wax flower 17. Okay, there are 17 classes. Okay, in this flower. Okay, so I'm downloading this one, and also what I'm doing, This is the X and Y I will be getting. Okay. So let's execute this one. It will automatically convert to your NumPy array. Okay. So you are not supposed to actually worry about. It is like ready to use data, because just for experiment, you can use ready to use data, because if I load my raw data right now, it will take time to pre-process and all. Okay. That thing will be showing you whenever we'll be completing all the architecture. Okay. Like ResNet Inception will be covering all the thing. Then we'll be like showing how to use your own custom data. Okay. We'll be creating dark cat classification, flower classification. These are the thing we'll be doing. Okay. Now, if you refresh here, if you see it has downloaded data, 17 flower data, and inside JPG, we'll see all the flower classes. Okay. All the flower classes. If I open any flower here, so this is the flower. If you see, this is the flower. Okay. So these are some different flower, and you have now, if you just print X here, okay, so you'll get a NumPy array. See, it is already converted to NumPy array. Okay. And Y is also converted to your output format. Okay. See, one-hot encoding. The same thing we did here. Okay. LeNet, I need to manage session. See, the same thing we did one-hot encoding for output. The same thing we are doing just by giving this argument. One-hot is equal to true. Okay. So now we have my data. So now what I need to do, I can show you the shape, X shape, how many data we have. And it is RGB image. I think you already saw. So you have 1360 example in a test data, your X data, and the image shape is 224, 3. Okay. But what is the input shape? My Alexnet takes, if you see, it takes 227, but I have 224, right? So instead of passing the input layer 227, we'll be passing 224 because I have this data. Okay. You can also pass it, no issue. Okay. But if you have 227 data, you can pass it, no issue. But either you can do one thing, you can reshape this data also. It's fine. But I will pass it as it is. Okay. So that's why I'll be using this one. So now let's see my Y. So Y shape is like, it would be same, 1360. And I have 17 actually flower example. Okay. So now, first of all, what you need to do, you need to create a sequential layer. Okay. Sequential layer. Now let's open our, this one. So here, after sequential layer, what you have a convolutional layer. Okay. So now let's build this convolutional layer. And yeah, so let's build this convolutional layer. Okay. So this is the convolutional layer. So in this convolutional layer, let's see, the filter size was a little bit, let's do it a little bit bigger. Okay. So here you had kernel 96. Okay. 90. Yeah. Channel is 3 because it is RGB image. Got it. But previous one, handwritten one, it was not RGB. That's why we took channel as 1. Okay. Now if you see, it is it has 96 kernel, that means 96 filter, stride 4, 11x11 filter size. Okay. We took the same thing here. Okay. We took the same thing, 19.6 filter. This is my input size of my image. So image input size, I'm taking 24 to 24y because my image size is like that only. Okay. So that's why I'm taking. And the actual image size is 227. Okay. But I don't have my that data. So that's why I'm taking this one. And kernel size is 11x11. I'm defining. Stride is 4. Okay. Padding is none. That's why I'm giving as valid. Okay. And activation function is relu. Okay. Make sure you're giving activation function is relu because they have introduced relu instead of tanh. Okay. So this is my first convolutional layer we have made. Okay. Now let's see the image again. And I need to pass it to max pooling layer. Now let's create the max pooling also. So pooling you can create. And yeah. And with the pooling, they have also told you to add normalization layer. Okay. So I am taking one normalization layer after max pooling. Okay. After max pooling, I'm taking one normalization here. You can either take here also. You can copy this and you can take here also. Okay. But I saw like many people actually they create architecture in that only. Okay, so what they did after max pooling, okay, they took best normalization. After convolution, don't take best normalization. Okay, this is the recommended because research proved that after max pooling, if you do normalization, your model can learn in a better way. Okay, and after convolution, if you take best normalization, okay, you may lose some information. Okay, so that is why it's recommended just take best normalization after max pooling. Okay. So max pooling, I had pool size 3 cross 3. Let's see. Pool size 3 cross 3 straight is equal to true. Okay. See, 3 cross 3 straight is equal to true. No padding. That's why I've added valid. Okay. Now, my start layer, it was again a convolutional layer, 5 cross 5, padding to 256 kernel. Okay. Now, let's take this one also. Yeah. So 256 kernel size is 5 cross 5, stride 1. Okay, because if you see stride 1, it was here I think they have mentioned stride is equal to 1. Stride is equal to padding. Yes, stride. Yeah, if you see, divided by 1, see stride is equal to 1. Okay, so that's why I've defined 1 here, and is equal to same means you are taking stride. Okay, that's why you are giving a same. Okay, and activation function you are taking relu. Okay, that's it. Now after that you again will pass this data to your max pooling layer, and max pooling layer will have 3 cross 3 pool size and stride is equal to 2. Okay, now let's take this one also, and after that you can add batch normalization, otherwise you can't add. Okay, it's up to you. So I'm taking again max pooling layer 3 cross 3 stride 2, valid, no padding, and batch normalization I'm adding. See, you don't have to visualize the image. Okay, you don't have to visualize the image. So see, image is a pixel. I'm converting this pixel. Now, the basics thing you have learned, the kernel, how kernel operation will go on. I think that thing actually sir taught, because these are the basics thing I'm expecting. Okay, let me show you one. See, in the backend, it will going on like that. This is your kernel. This is your image. Okay, and that's how it's doing the convolution. See, this thing I think you have learned and even confirm, because I'm expecting you know basics. How convolutional happen? No, you can't use 10H because they have introduced ReLU. Okay. They have introduced ReLU. See, everywhere I'm using ReLU. Okay. Don't use 10H. Got it? That's why this is different. Nah, LeNet is different. Alexnet is different. Why? Because they have changed this parameter. They have added some extra layer. That's it. Okay. Even you can do some modification. You can create your own architecture. And I want to give some assignment. Just modify this architecture. Try to change this parameter and see the output I'm getting from the actual Alexnet. You can improvise or not. Okay. If you want, I can give you this visualization notebook. Okay. You can refer anytime. So now I have added my pooling layer also. This pooling layer I have added. Now again, need to pass to convolutional layer. So now let's take convolutional layer again. Yeah. Again, let's take convolutional layer. Okay. This is the convolutional layer. And there is a little experiment. I added it extra. Okay. I took a batch normalization here. Okay. You can take either, you can drop it. Okay. Then after that, again, you can see Max. Then again, I need to pass a convolutional layer. Okay. So now let's again take a convolutional layer here. number 4. Okay. Then again, I'm taken one batch normalization. Okay, you can take either you can remove. Because see, this is not a hard rule you need to take. You can remove it also. It's fine. But the architecture would remain same. Okay. Then again, what you need to do? Again, you need to pass to again another convolutional layer. Okay. So now let's pass it to another convolutional layer. Okay. And if you see those parameter are same, I'm taking this parameter are same only. Okay, just relate with this image. Okay, this code you will get it. This parameter is remain same. 184 kernels. Okay, then 256 here. So 256 here. Okay. Then again I need to pass to the max pooling layer. So let's do it. So max pooling, yeah. So this is the max pooling layer. Okay. Max pooling, and max pooling will have 3 cross 3. So it will have 3 cross 3 straight is equal to 2. It's fine. Okay. So now once everything is done, now what you need to do, you need to pass to a flatten layer. If you see, once you are here, so you need to pass to a flatten layer. Okay, so now let's create a flatten layer. This is my flatten layer. And now what you need to do, you need to pass to your FC layer, fully connected neural network. Okay, and it will have 4096 neuron. Okay, then again you need to take another fully connected. It will have 4096 neurons. Now let's take it also. So yeah, so let's take it. So if you see, I took, first of all, this is my first dense layer. Okay, this is my input shape I'm defining. Okay, then I'm taking activation function as relu, and I'm adding dropout. It is not mandatory. You can add dropout, either you can remove it. I already told you. Okay, there is no hard rules. Okay, you need to mention dropout. Then I have again added a batch normalization. Either you can remove it, you can keep it. It's up to you. Okay. Then the second dense layer, I took 4096 because here it is mentioned 4096. Okay. Then after that, I took ReLU activation function. Again, I added dropout. Dropout value I've given 0.4. Okay. Then batch normalization I have added. Okay. Then after that, I have done each and everything. Now I just need to add the output layer. So how many output you have here? Anybody? What is the output you have in this example? Yeah, 17. Okay. So that's why at the last layer, I will be taking 17 output, and my activation function would be softmax. Okay. Then I want to print my model summary. Now let's print it. And you will see, like, you will have trainable parameters, like it's very big. If you see, just can you please see around it's like millions of parameter you have, right? Dropout is a layer. It will help you to, you can say, reduce the overfitting. Okay. I think it can be taught in the class. I'm expecting dropout has been taught. Guys, dropout. Okay. If you miss the session, so just try to refer. Okay, dropout is a concept. It will reduce the overfitting condition. See, if you want to calculate, if you want the calculation, just just refer this image. Just try to visualize in your mind. Okay, because this thing has been covered. I'm expecting basics has been covered. So don't ask for the basics right now. Okay, if you just want to refer, just see the visualization. Every calculation is going on. See, in an animation way. Just try to see. It is also using 3 cross 3. See, 3 cross 3 filters. It is utilizing. Okay. So assignment, what you can do, you can change this architecture. So see, now I'll give you, like, what is the assignment. Now let's see the accuracy we are getting, accuracy we are observing. So this is my trainable parameters. Okay, this is my trainable parameters I have. Okay. So now let's start the training. So first of all, let's compile my model. Okay, so I am taking an Adam optimizer with the learning net of 0.01. Okay, and I'm taking categorical cross entropy again. Okay, metric is equal to accuracy. Now execute. Okay, then now let's start train our model. Okay, so I'm passing my X and Y data. Batch size 64 I am defining. Epochs 5 I am defining. Verbose is equal to 1 means you want to see the logs. Validation split. 0.2, that means 20% you want to keep it as a validation set. Okay, so whenever you will see validation accuracy, validation loss, you'll be using this data only. It will automatically do that. Fit method automatically will validate if you are not passing in that way also. So here we have passed, can pass like that also. Okay, it is also possible. And shuffle is equal to 2 means you want to shuffle the data, okay, every time. So now let's execute. Now you will see like it will start training. Okay, so accuracy, you can see it's like not very good. Okay, because I use just 5 epochs, so you can increase the epochs. Okay, so now your assignment would be change this parameter. Okay, change this architecture a little bit. Suppose just add 10h here, like change this kernel size, change the stride size. Okay, then instead of giving best average pooling, just max pooling, use average pooling, and try to achieve, like you can achieve good accuracy or not. Okay, you can use any data, you can use MNIST data also. Okay, you can use this flower data also. Just try to do it. Okay, then whenever you're playing with this architecture, okay, so you will, it will be very clear in your mind, and you will feel like I could have implemented this architecture, okay, by myself. Okay, so that is how actually research happened. So people, what will do, they will take this architecture only, they will change some parameter, they will name it, and they will tell like, yeah, I've made this architecture if it is performing good. But the condition is it should be performing on the ImageNet dataset. Okay, so I think Alexnet is clear, all of you. Just confirm. Implementation wise, theory wise, I think it should be clear. Okay, just always refer this picture, always refer this picture, just keep it up. Okay, that's it. Data augmentation, I didn't apply it. You can apply. You can, data augmentation is what? You can do some zoom operation. You can crop the image. Okay, data augmentation. Let's show you us data augmentation. They told you to do that. If you're doing that, you will get good results. Okay, you can do it. See, this is the data augmentation. See, they're removing some, decreasing some brightness. They're increasing the brightness, contrast. Okay, saturation. That's how they're making different variation of the images. Okay, that is called data augmentation. They're also, see, rotating the image, zooming some image, cropping some image. Okay, that's how we can do the data augmentation. Yes, I will upload all these class notes. Okay, I will give it to Sunny sir. No issue. Yes, I will share the note also. No issue. Everything you will get. Okay. Now just tell me, are you able to understand this session or not? How was the teaching? Like, it was good. Like, make sense everything. Am I able to like make you understand? Yeah, thanks. Just give me a minute. I got a call. Yeah, sorry guys, I got a call. Yes, thank you. Thank you for your feedback. Yes, I will teach you casual data set. We'll be taking the raw images and we'll be doing. Okay, no issue. Don't worry. just try to understand the architecture first of all. Once you have understanding the architecture, at that time we'll be focusing on the data part, because that time you won't have any questions on the architecture, like what architecture we are using, how it is working. Got it? See, ResNet is a architecture in CNN, convolutional neural network only. Okay, it's a like variation of this Alexnet only. Okay, ResNet, we have added some more layer. We have added some skip connection. Okay, that's how we have made ResNet. Okay, so tomorrow agenda, we'll be discussing about the VGG. Okay, VGG net. So there are two kinds of VGG, VGG 16 and VGG 19 is there. I don't know. I'm not sure. Tomorrow, Sunny sir, we will going to take the class or not. If he is coming, then it's fine. Otherwise, I will be coming. I am not sure. Is there a holiday? Okay, if you want me, you can. Mm, So you'll be sending me then. Yeah, I'm sharing my mail ID. This is my mail ID, and I'm sharing my LinkedIn profile also. You can connect with me. This is my LinkedIn profile. And if you want to learn more about computer vision, I had some YouTube playlist also, like YOLO V5, YOLO V6. Okay, this is my YouTube channel. You can also add me here. Okay. See, doubt, you can join the our all the doubt clearing session. See, deep learning is expensive task, right? See, deep learning you are not supposed to apply every time. Suppose if you're working with tabular data, at that time ML algorithm is fine. But whenever you are working with the non-linear data, suppose image, speech, okay, this kinds of data, apply deep learning. Got it? Because deep learning here you are using non-linear, like you can say algorithm. That means neural network you are using. Okay. But in machine learning, it's a statistical learning. So tabular data is fine. It's a linear data. Most of the data you will see. But image, text, it's a complex. Videos, okay, it's a complex data. It's not a linear data. Okay. So that's why we use this kinds of DNN, deep neural network, like CNN, RNN, okay, NN, this kinds of architecture we have. Yes, yes, hands-on, you will get each and every topics, no issue. I think this two algorithm you also get hands-on, right? Now, how to work with your custom data will be also teaching, no issue. Actually, previously I used to publish on in Bengali, but nowadays actually I'll be everything will be published in English, no issue. Okay. Because when I get time, I just try to create some content so that. Okay. Okay, guys. So I think it's fine with you, everyone. Let's end up the session. Okay, because I just need to go somewhere. That's why I'm a little bit hurry. Okay. So and we take the doubt. Okay, if you have doubt, just connect with me later on, or otherwise you can join that live doubt clearing session. Okay. because I had some product. Okay, so they're calling. I just need to go to the market to receive the product. So that's why I need to go somewhere. Still, like you have object detection, segmentation. Okay, then GAN is there. After that, you will be starting with the NLP. Yes, big data. I think it would be also there. No issue. You can send via mail also. Otherwise, you can. Uh, Actually, tonight I will be in the doubt clearing session 9 to 12. Okay, if you want, you can join there. Okay, your all the doubt clearing session. Okay, guys, then let's drop up. Okay, thanks for joining the session. Hope you have enjoyed. Okay, and just keep learning. Don't like be inconsistent. Okay, if you are consistent, then it's like it will be very easy for you. Okay, to learn each and every concepts. Okay, but suppose you are picking a concepts and you are like doing it. Okay, after 2 to 3 days. Okay, it would be very hard for you. So just try to learn as much as you can. Try to do explore. Okay. Yeah. Okay, then. So bye everyone. Thanks for joining the session.